Okay, so we just finished up talking about calculating a correlation coefficient by hand as a way of understanding that in a regression model, the relationship between variables is nothing more than the average cross product of those variables, right? Or at least in terms of the standardized regression coefficient is the average of the standardized cross product of those variables. And in truth, the unstandardized is also the average of those cross products, but it becomes a bit more convoluted. So it's easier to stick with, at least for right now, the standardized version. There's also some other important reasons to stick with the standardized version. Anybody want to guess why? Or what is the benefit of using the standardized version? It's super easy to interpret, right? Like a correlation of 0.2 or 0.4 means the same thing across data sets, across situations. We can understand that it's a magnitude of effect that is the overlap of the standard deviations of these two variables, right? What is the problem with interpreting them completely in terms of standardized correlations? Or standardized overlap, I mean. Standardized products.
You have to like convert it back to the raw score to actually understand what that means.
They don't have that's exact. They don't have real world meaning to us, right? If I say that an increase of 1 standard deviation in time from PhD results in an increase of 0.65 standard deviations of publication, what does that tell you about anything related to the number of publications that a person would have 5 years from their PhD? That's like nothing. You can work backwards from the math, but it's difficult to do that. This is, and what is the point? I said this in the video. What is the entire point of statistical analysis, of inferential statistical analysis? It's to understand why things vary from the mean, right? To understand why everything isn't 19.93 or whatever, right? And so the one of the reasons that somebody's publications are not 19.93 whatever is the distance they are from when they got their PhD. And in order to figure that out, we plot this line and we get our best guess of what their publications should be. And regression analysis is trying to come up with the best guess. And by doing this, how does it come up with its best guess? It plots a line that does what? We say it plots the best fitting line, right, through our data cloud. What do we mean when we say the best fitting line? It's trying to maximize something, right?
Minimize the error.
Yeah, minimize the error, right? And so we're trying to, and another way of saying minimize the errors is minimize our residuals, minimize our difference between y and y hat. Let's look at something here really quick. Actually, before we do that, no, let's do that because I don't want to lose track of what my train of thought here.
Are you recording?
Yes, I'm recording. Thank you. David, you missed your cue. No, that's okay. Let's flip back over and let's look at SPSS. I'm going to do this in Stata just real quick, just so because I know how to do it fast and easy. But if we look at a scatter plot of these things, that's what our scatter plot looks like, right? And we're going to plot a regression line that goes somewhere through this scatter plot. And actually, okay, throughout the semester you're going to find this out. I am not an SPSS person, but I'm trying to do this in SPSS for you guys' sake. So sometimes you'll have to bear with me a little bit. Let's go graphs. I don't even know. Okay, yeah. Is this a scatter plot? Scatter. Perfect. Oh. Do I have to grab this and bring it up here? Is this how it works?
There's an easier way.
I'm sure there is.
Yeah. Right.
Does this work? Let's see if that works. Okay, that's my scatter plot. That worked, right? And I know that I can double click on this thing and I can get my chart editor and I can do elements and interpolation line. Is that right? Maybe not. Ooh, that looks not what I wanted. Oh, I wanted to fit line. Let's try this again. Oh my goodness. Now it looks terrible. Okay, somebody walk me through. What is the way to do this?
Graphs.
Graphs.
Legacy dialogues, and then it says scatter slash dot.
Legacy dialogues.
Second to last.
Scatter slash dot. Thank you. This is much easier. Y-axis is our publications. X-axis is time. And will it? No. All right, so we get the same thing here. I thought that in elements I could, do I need to do this? Will this do it?
There's an add fit line.
Yeah, under elements, right?
Just above the graph. It's there's kind of,
Oh, is it this guy
yeah,
here?
that guy.
There we go. Thank you. And it gives us our regression equation right here. We've already seen this, right? And so we have these values here that are our actual y values, right? And if our values all sat on this line, they would be y hat values. Y hat is the perfect prediction of where y should be based on x, right? And so, let's go back to SPSS here for a second. Good, that puts that in there. Let's grab our z-scores that we calculated here. And let's just paste those straight into our data here. And we need to rename those. The first one was ZPHD, the second one was ZPubs. Okay. So I had said just a moment ago that the correlation between x and what is the correlation between x and y? We've already looked at this. It was the first thing that we did. What was it again? What's the correlation between pubs and PhD? 0.67. And so that is the correlation, assuming that we don't have perfect fit. If we did have perfect fit, then y would be on that line all the way down the line, right? And that means that our predicted value of y should always fall on our line. And if our predicted value of y falls on our line, it is perfectly predicted by x, which means the correlation between x and the predicted value of y is what? Should be 1, right? More importantly then, the correlation between x and the residual value of y should be what? What is the residual? It should be 0 because we are removing everything that every aspect of y that's associated with x. Let's test this. let's go analyze, correlate, bivariate. X is time since PhD, right? And let's put unstandardized predicted, unstandardized residual, and let's hit go. And we can see right here, time since PhD, the correlation with our predicted value of y. And what is, again, what's the name of our predicted value of y? What do we call that? Y hat is 1. That is the perfect relationship between x and y. And the residual of y, which is y, the difference between y, where we expect y to be and where y actually is, removes all of the variance in y associated with x, and consequently, the correlation between the residual, where is that, and y is 0. There is no correlation, right? And that's exactly what we should be finding. So regression models are fitting a line, a best fitting line, and the predicted model assumes a perfectly fitted line, right? All right, back to our regression equation here for a second. Let's do an exercise. Let's say that you are 8.7 years since you got your PhD. How many publications should you have if you are 8.7 years since getting your PhD? Yeah.
8.7 years times 1.98.
8.7 years times 1.98
plus 4.6.
plus what?
Plus 4.7.
Plus 4.7, okay. And so, what is that? Should we just, I was gonna make you guys do it, but I'll just do it. Equals 4 point, is that what it was? 4.78? 4.73 plus 8.7 times, what was our slope? What's that? 1.983. 21.9821. Let's pick a number over here. So that is what you should be. And if we look at our graph here, then how many years did we say? 8.7? So yeah, like right here, right, is where we're kind of expecting a person to be, and that looks about right. 21.9, about 22. I suppose that's right. All right, let's pick a value of PhDs. So this person here, actually let's do 10. This person here is 10, so equals 4.73 plus 10 times 1.98. Is that right? Close enough. This person should have 24.53. They don't. They have 48, right? If we go equals 48 minus 24.53, we get 23.47. That's this dude here, right? Yeah, so this dude is probably an outlier. I say dude, could be, I mean, this person. I shouldn't just say dude. So here they are, 10, 48, predicted value, 24.56. That's what we got. Well, there's some rounding error there, right? 24.53. Residual, 23.43. 23.47. Again, that's because of rounding error, but we can calculate out those residuals ourselves, right? By using the regression equation that we've got, finding the predicted value and subtracting that from the actual value, and then we'll know how far that person is away if we wanted to know that. Then we can find the, if you want, we can go through and find the average residual, right? And we can know that a person's average score, or a person's predicted score, in this case was 24, and that there is, based on the average error, the average residual, we can calculate confidence intervals around that, right? To determine if that person is, how far away from the average score that person really is, if they are significantly away from the average score or not. We're not going to get into that. That is in the text, but it goes beyond what we want to do, at least for today here. The point of all of this is that we can use these regression equations to get a best prediction of where we think a person should be, with the idea that there is going to be some error around that, right? We will not, in all likelihood, won't predict it perfectly. Though if we look at our graph, there are at least a couple that are pretty close to being predicted perfectly, right? But the vast majority are not. I don't want to get too far ahead. I wanted to talk a little bit about, so in the video for today, I talked a little bit about assumptions, and I just want to make a quick point here, because in stats, in ARM 1, you guys learn about basic assumptions for inferential statistics. And what are our basic assumptions for inferential statistics? There is one that everybody mistakes, and I want to make sure that we understand that this thing that everyone says is an assumption is not a real assumption of inferential statistics. What are our basic assumptions?
Values are fixed.
We have fixed values. What else? What are the big ones that everyone says? What's the first one? The first one that everyone says that is, what's that? Normal distribution. I'm going to come back to that. Homogeneity of variance is usually, actually, normal distribution is the one that everybody says. I'm always wrong about it. Drives me crazy. Let's come back to normal distribution. Let's talk about homogeneity of variance. What does homogeneity of variance mean? Yes, equal variance either across groups or across values of x. If we don't have that, what is that called?
Heterogeneity.
Say that again?
Heterogeneity?
Heterogeneity or yeah, and so we often see it kind of splayed out as like heteroskedasticity, right, in our charts. The idea, though, is that our variance should be roughly equivalent across time, and I had, in the video, I had put some graphs to differentiate between homogeneity and heterogeneity there. What is another assumption that we have about our data? And the second, I would say the second most important thing, we have one called independence of observations, right? And this means that each observation comes from an independent source or observer, right? You don't have the same person reporting multiple times within a survey or something along those times. If you do, then you're violating this independence of observations. The reason that that's important is because you wind up having clusters of relationships that are not due to random distributions, but instead are due to a factor outside of random distributions, right? It's a non-random cluster of scores. Let's talk about assumption of normality. One, linear regression, and even more so when we get into maximum likelihood types of models, are very robust to non-normality of the predictor variables and the outcome variable. But when you have non-normal distributions, you run the risk of having a non-normal distribution of residuals. And this is what we mean when we say a normal distribution. We're not talking about a normal distribution of the actual independent variables or the dependent variables. That is less important. What we want is a normal distribution of residuals where you have most of your residuals clustered close to 0 and a random distribution extending out from 0 in both directions, both positive and negative, so that your distribution, or so that your residuals form a normal distribution. There are ways to test that, which we will get into in 2 classes, not next class, but the following class. We're going to look at examining distributions of residuals. But I wanted to make sure and highlight that today, that it's not, when you review articles or something, in fact, I was just doing one with Mike, and Mike was saying a reviewer had complained about they didn't complain, they asked for information on the distribution of the variables, and I said just throw it in there, and he was like, well, this one has some skew and this one has some skew. I was like, it doesn't matter, like who cares if they have some skew? If the residuals are normally distributed, then it doesn't matter. And they were, and it didn't matter. And so, but that is the actual assumption, a normal distribution of residuals, not of variables. So it's important to understand your residuals. I think that is everything that I wanted to cover today. I know that we're done, but are there any questions that you guys have of me?
That's why the outlier makes sometimes a problem?
Yes, that's exactly why outliers become problems, right? It's because when you have an outlier variable, especially in a bivariate association, it winds up being a huge residual that can pull the distribution of residuals out of. And we form our standard errors not based on the distribution of our variables, but our standard errors are formed based on the distribution of our residuals. So the tests that we have of our coefficients are all a function of the distribution of residuals. And assuming we have a normal distribution of residuals, then we can use a normal t-test, we can use a normal standard standard sample to test our parameters in our model. If our residuals are not normally distributed, then things like t-tests and f-tests and so on are no longer valid. We're not meeting the assumptions that we have to make those claims. Yeah. So let's talk a little bit about what the homework is going to be this week. I have a data set. It's uploaded. I have to make it live. I didn't know how far I would get, so I have some questions in there, and I didn't know if I would add questions or remove questions based on that, but I'll make it live later on today. It is data that has behavioral inhibition and behavioral activation and affect lability. In there, you're only going to be looking at affect lability and behavioral inhibition for this week, but I want you guys to get familiar with the data set because you'll see it again. And what you're going to be doing is, just like what we did in Excel today, you're going to calculate the correlation coefficient, then you will run the correlation coefficient in in SPSS. You can provide the output for that. You can just copy and paste the tables over. The questions will be self-explanatory. Similarly, you can just copy and paste what you're doing from Excel over into Microsoft Word. And then the last thing is I will ask you some questions about the stuff that we talked about today. But more importantly, when it comes to the data, I will say, okay, so if somebody has a raw score of this for behavioral inhibition, what should their score be for affect lability? And you can calculate that by finding what? You enter it right into your regression equation, and the answer is going to be the y hat for that regression equation, right? That's a predicted value, though. It's not an actual value. The last thing that you guys will be doing is there's a question that asks, person such and such has a value of this, and their predicted value is this. What is the difference between their predicted value and their actual value, and how do you find those, aside from just saying, give me the residuals, right? So put it into a very simple kind of equation or something, or just describe it. I didn't even care, right? Just describe it, that's fine. I know in the syllabus it says that you guys will write results sections for each one of these. We're not quite at that stage, so we're not going to worry about that. We will get there by the second half of the semester. It will be results sections, but right now it's just going to be some simple questions about the analyses that we did today. So today we covered correlation, and mathematically, what is a correlation coefficient? Somebody tell me, what is it mathematically? Mean standardized product. That's exactly what it is, right? It's a super easy way to think about it. You convert 2 scores into z-scores, multiply them, divide by n minus 1. And that gives you your correlation coefficient. Also, that will be in your homework. Any other questions? No? Enjoy your weekend. There are some great football games on this weekend. And we will pick this back up next week. If you have any questions, concerns, comments for me, shoot me an email. Otherwise, I will see you guys next Thursday.